So the previous lesson had talked about aggregate operations in general, and I distinguished between kind of run to completion operations and short circuit operations. What we're going to do now is we're going to go a little deeper into examples of short circuit operations so you get a bit better feel for what they do and how they behave. So keep in mind that an aggregate operation may process all elements in a stream, much like the water purification system analogy I've used many times. So the water flows through from beginning to end and is purified through different filters along the way. And that's what we would typically call run to completion operations or run to completion semantics. A good example of run to completion is the map intermediate operation, which processes all the elements in its input stream. So a stream comes in, the map method runs the mapper on each of the elements, and then it generates the output, which is the mapped results of applying the mapper function to each one of those, all the transforms. Of course, there's special cases. If the mapper function happens to throw an exception, and that exception is not caught and swallowed by the mapper function, then you can have a stream terminate abruptly, even though it's calling map. So there are ways to get streams to stop, but in general, that's considered to be somewhat awkward. And that's one of the interesting areas of streams that may be a little bit less intuitive at first glance, is dealing with exceptional conditions. You ideally want to minimize them as much as possible. And if you have lots and lots of exceptions in the types of programs you're writing, you might consider using other mechanisms, other parallelism frameworks that Java offers, such as completable futures, which handle exceptions in a more seamless way in some sense. In contrast to the run to completion operations, short circuit operations halt further processing after some condition is reached. So one example, which we'll talk about later, probably next time, is the takeWhile intermediate operation. And this is an interesting operation because it's a stateful intermediate operation that's short circuiting. There are only a handful of them that are stateful and short circuiting. takeWhile is one of them. And what it does is it will continue to do its processing until the predicate no longer matches what's in the stream. So you continue to do something until the predicate no longer matches. So while the predicate matches, keep doing the processing. There's also a dropWhile, which is kind of the inverse of that. We'll talk about that later. Limit, we've talked about that before. That's a short-circuiting intermediate operation that causes a stream to operate on a reduced size. So what it'll do is it's also stateful because it has to keep track of how many elements it's seen. And you pass in a parameter, which would be whatever the max is that you're willing to handle. And once let's say the max is 100, once the stream's framework realizes you've processed 100 elements, it will then say, okay, we're done, no more processing from this stream, and we're going to essentially break out, if you will, and we're done. So that's kind of like having a loop that is iterating from 0 to 100 or 0 to 1,000, and you have an if statement in there that says, if this is the 100th element, break, right? So that's kind of the equivalent of what limit does. And in fact, that's one of the reasons why the actual semantics of streams work using this top to bottom, left to right semantic rather than a left to right, top to bottom semantic, because that way you can have these short circuit operations that are just as efficient as if you'd written them using loops, because they'll break out at the right time. There are also a whole slew of these short-circuiting terminal operations, find first, find any, none match, and so on. And I mentioned those before, and they basically will stop processing the stream as soon as the condition is either met or not met, whatever the condition is looking for. So if you use the none match terminal operation and there's a match, it can bail out at that point because it cannot ensure that it no longer it knows it can't have the condition none match enforced for the whole stream because we found something that didn't match. So that's the end of the overview of short circuit operations. Very useful to know about these things and to be able to use them effectively. As we will see later when we start talking about parallel streams, there's some limitations on the short circuit operations when run with parallel streams. And that's because short circuit operations have implicit dependencies on things like counting the number of elements or keeping track of how many things have been seen. And parallel streams work best if there are no dependencies. And even though parallel streams will work correctly when used with short-circuiting operations, they may not necessarily work efficiently. And so the wisdom of being a good developer in general is to know the limitations and the pros and cons of the different mechanisms under different configuration assumptions or conditions, and be able to choose wisely so you don't end up with a program that works but is unbelievably inefficient or space consumptive, thereby alienating your user base and disgracing you in the eyes of your colleagues. So that's the overview of the discussion of short circuit operations.